Hi, everyone. Welcome to another episode of the Haskell Study Group. I'm your host, Ram Vedam with Atlanta Functional Programming. My apologies for starting so late tonight. Sometimes the real world, gives us some things and prevents us from starting, things as scheduled. But we're gonna get stuff going here today. And since today is going to be a review day, I thought it would be okay. Uh, so the last couple of weeks we've covered the essence almost of Haskell and what a lot of folks promote as being the core features of Haskell. And that is these notions of type algebras. All right. Specifically, we started, if you recall, with semi-groups, which is the beginning of it all, if you will, where the idea of a semi-group is essentially any type class instance that adheres to the semi-group essentially implements something that provides associativity, right? It's a function that, given how you implement it in your type class uh, instance, it will allow you to do function application and preserve the property that no matter where you put the parentheses to group the application, the end result of the actual application is going to be the same. Um, Folks who are on the Jitsi call, if you guys can, put yourself on mute, that would be most excellent. I would appreciate it. Um, we then went on and started talking about monoids. All right, monoids introduced on top of the associativity this notion of identity. Right, and remember, if you recall the identity stuff, basically that means anything that um, you apply the identity operator to will return itself back. All right, and we've looked at some examples of this in particular, if you recall, the semi-group, we actually have this notion of this associativity operator. That's the brackets operator. That's an infix operator, and on top of that, we have built monoid, which includes the functions mempty, which is your identity operator, and uh, mappend and mconcat, which both deal with the associativity semantics, in which specifically in how things will reduce to the final type that you're actually implementing the monoidal operator for. Now, remember, with semigroups and monoids, specifically with monoids, we had to preserve the properties of left identity and right identity, which, although they're technically the same application in terms of the end result, they are very different operators because the ordering of the arguments have been changed, right? So, if you recall what we talked about here in this example, and let me just change this. Uh, in our left identity and right identity, we have this notion of providing this empty operator, which takes no arguments and returns the identity type for that particular type class instance. And if we apply mappend to um, mempty and x, either when mempty is the first argument or mempty is second argument, for any given x, you'll always get x itself. All right. So um, we learned also that under construction, lists are the has the identity operator of the empty list, of course, and its associativity operator is a concatenation operator, which we've used as being the plus plus operator. All right. And we went through a couple of examples in there. I don't want to bore you with most of these details because we have these already provided to you at your disposal in our previous videos. Please go ahead and refer to them for more detailed discussions. I just wanted to point them out because in chapter 19, they went through some practical examples of these the usage of these, specifically using the Spock HTTP library. Now, I decided after reading through chapter 19 quite a bit that honestly, um, while chapter 19 focused a lot on the practical aspects of this, I don't think it will do. I would be able to do it justice because, as the chapter rightfully pointed out, Spock actually ends up having is a fairly heavyweight HTTP library. It has a bunch of features, and honestly, the examples it took me a while to actually understand what some of those examples were doing. Like I kind of understood where it was going, but I rather not incorrectly provide you some information on how sorry, not Spock, Scotty is the name of the web framework. Uh, just because, again, Scotty is a more full-featured web framework than what's available. And for those who are interested, there's actually a tutorial on Scotty available on Scotty's GitHub repository. All right. And yes, there is a related Spock Haskell sort of thing. I'm just mixing the two up. I didn't. I forgot that there was another one. The book was talking about Scotty. So folks who are watching us today, watching this, just remember Scotty is available. It is a web framework for uh, Haskell, but I really don't know beyond that, just because I haven't had a chance to really play around with how Scotty kind of works. I just tried to work through the examples from the type signatures that were provided. Um, One of the things I wanted to bring up today, although we are covering, I was not necessarily examples that was brought in by chapter 19. I think because, again, I think most of you can uh, read the book and get uh, some better understanding of what was available. But one thing I wanted to kind of review was just a couple of points that we may have missed out last week when we were finishing up our Monads review. All right, and that is when it comes to Monads specifically, they're the one thing that you want to make sure that you remember is that you are preserving the laws that we talked about. Okay, remember what a monad actually is. In a sense, it is just nothing more for folks who are trying to look for a simple term. Think of monad specifically. The bind operator has a concatenative map. All right, and a monad is nothing more than a, an applicative. All right, and more specifically, they call it as an applicative functors, but in the book, but an applicative is a functor, so I really don't know why you would have to say that it's an applicative functor, right? And the specific laws that it actually preserves is much like the laws that we saw with applicative, mainly identity and associativity is two of the main ones, and you also get um, uh, interchange as well as uh, if you look at our sorry, our applicative overview here, we have homomorphism and interchange. Right. And homomorphism is taking advantage of the fact that we have essentially something that lifts our stuff into this applicative world in the case of pure, and we'll be able to actually run the function on a value once they're lifted in the same realm, much the same way as if we applied the function first and then constructed the actual applicative or monad at the same time. And as we saw last time, we saw that this really helps us as we sequence one or more operations using the do syntax. Now, of course, you could use the space uh, operator. Sorry, the the sequencing operator that is provided by applicative, or the sequencing operator that's provided by monad. But at the end of the day, the behavior is going to be the same, right? The one thing that I was thought that would be pretty interesting is this example that was actually covered that really drives everything home from the monad kind of chapter. And this is straight up the case study that was end to end. A lot of this is just code uh, that we can actually see from the GitHub repository. Um, and I thought we would just go ahead and download this guy and check it out ourselves. All right. Um, Give me just one second here. So first, let me go ahead and go into my shell and let's go and clone here. Get clone uh, this guy. Here we go. Um, so Shorty Prime is basically a a simple example of shortening a URL. All right. And the one thing that we want to first start with is, and I actually probably forgot to include this, is for folks who are trying to write their own version of this and follow along, um, the Shorty uh, service is actually it will start with using its cabal file. It actually depends on a couple of different libraries, specifically byte string, headers, MTL, and so forth. These things that we're looking here are the ones that are probably going to be used by us in other future projects. But I think it's important that if you want to pause this and go through this cabal file, by all means go for it. Again, these uh, GitHub URL, which is available, is on the previous screen when I did that clone. That is what you can use to actually go and review this code, so you don't have to necessarily write it. Um, I thought it would be useful for us to actually go through um, in main.hs is the signatures that are available here in terms of uh, I'm sorry, there's a question here, comment about Haskell to WebAssembly. Um, okay, could you be more specific to your question? Okay. Um, okay, so there was a question about Haskell and its compilation. Yes. So GHC, the core Haskell compiler, is a compiled language, will compile to machine code. Um, there are backends to generate JavaScript, if I remember correctly, as well as WebAssembly, but don't quote me on that. I encourage you to go and look it up. I'm pretty sure actually there is a WebAssembly target. I just don't know how to invoke it. Uh, uh, yeah, so I haven't actually tried it myself. If there isn't, folks who are watching, put the YouTube comments, all right? Correct me if I'm wrong. I'm pretty sure GHCI has one, GHC has it, but I could be that my memory is probably mixing up a couple of things. I'm speaking off memory, so sometimes that could be incorrect. Um, Let's go through this repo. One thing to note for folks who are doing the Cabal stuff, Stack makes it easier, and yeah, obviously the uh, while the libraries will be curated, it will guarantee to work just because their goal is to make sure that you have stable versions of all the libraries that you're using for a particular version. Um, so the one thing to notice about this before we begin and do a code review of this is um, just like we used other examples of this, but line one is a language extension. All right. Overloaded strings is a new language extension. I don't think we've used it in the past. Basically, it makes polymorphic strings much in the same way that numerics, if you think of uh, num type class, yeah, it allows numeric literals to be polymorphic and be of different numeric types, right? Um, String, remember, itself is not normally polymorphic because a string in the vanilla Haskell sense is nothing more than a type alias to a list of characters, all right? String overloaded strings, the language extension basically changes um, uh, the type in a sense, in that a string literal now is treated as a text object value or a byte string object value. All right. Um, just keep that in mind. Um, One thing I think is important to show is probably to illustrate this. And the best way to do that is firing up Haskell itself. So let's go ahead and do that. Buddy, stack. Oh, let's go ahead and download a bunch of stuff here. Oh, geez, that's a pretty big project. Um, let's see what it is grabbing. It's grabbing a bunch of different libraries. Wow, I thought there was only 10 major components in here, but this looks like a fairly extensive library. All right. Um, This is interesting. There seems to be several different libraries that were downloaded and need to be compiled for the components. But while this is work going on, I'm going to open up a different shell. Okay. Um, uh, that a different shell, but um, and, okay. You know what? I'm just going to make a shell here then. Um, it looks like I can't open up multiple shells, but that's kind of weird. Um, while that's compiling, let's go fire up GHCI. Okay, and let's just start again with um, string class again. All right. Um, if you look at the string class, there is a function called isString. All right, which is itself a type class that converts something from a string into a value, right? This is string type class is a way to actually convert literals to their particular appropriate types. And just like, much like actually the numeric type class, if you remember, the numeric type class has also um, this from integer function that basically converts an integer to some appropriate types and allows you to switch between different types. All right. Um, The type class, remember, is nothing more than an interface to some particular implementations. And sure enough, just like the numeric type, the string literals that we're going to be using when we use X overloaded strings, we're going to actually get a some interesting features around this. Okay, so let's kind of look at how this works. So first, I'm going to have to load overloaded strings into my REPL because right now I don't have overloaded strings loaded. So let's now try type one, and we'll see that, again, this is nothing more than a numeric type instance that's converts to P. But what about type blah? All right. Now here, um, you could see that it's taking in the isString type class, all right, and it adheres to it, and it's just returning its type. Okay. Now, what's nice about this is you can actually uh, with the overloaded strings, take a string literal like this, which is defined as text. And to see what text is, let's first, obviously see what text is. All right. Oh, sorry, t text. I think maybe. I thought info on text would be available. Let's see. There any data constructor on text? We'll see this. So one of the things about string literals is if you label them as the text data type, and you do from string on, say, um, I lost my cursor here. Um, I may have lost. It is not liking the fact that I'm using. Let me run this guy in the background. Hold on one second. Here, a window closed, so we can actually. All right. So, um, so, oh, sorry. So without the string type there, without the overloaded strings, because set minus x overloaded strings actually gets rid of the extension. We see that uh, the type of blah is just nothing more than something that adheres to the isString interface. Okay, but by putting this language extension uh, here and trying to do I think I could do this way in Haskell language overloaded strings. Okay, and then do blah text equals from string blah string. This will actually convert. Hold on a second. Not in scope type constructor data type. Oh, okay. Um, why is that not showing up? Maybe I'm missing something in my. Ooh, okay, that's probably why. Uh, import data.txt. Now, mm, okay, import data dot. Uh, that's weird. Oh, I misread this. Okay. So what this guy is doing here, when you do overloaded strings already, um, is that if we do a equals blah, right, and we look at type A, we're gonna get is string. But if we do, sorry, if we do GHCI and we do a equals blah here without overloaded strings and we do type A, we get a string of characters. Okay, that's right. All right. So the isString type class instance is brought in from overloaded strings. All right. And it actually comes into play when you are using strings which has text or byte string values. And what it does is when you use this language extension, it basically goes in and converts and creates a bunch of overloads for the different type conversion operators, all right? Whether it be from string or from integer or from rational, all right? One second. Nope. So now we see that before and after we do type A now, we'll see A is blah. But if we go and reinstantiate blah A, we check the A, you'll see that it's now converted into a from string operator that actually converts it into a string. All right. Which I do this string, string. Does it do? There's no string. String. Oh, right, because it's thinking of it as being so by doing blah text, okay, and we have to first import data.text. All right, by saying a equals blah text, TA is going to be of type text. But what TA really has done is behind the scenes is it actually called from string and converted that string into the text type that we wanted. All right. And text and byte string provides instances of this is string type class so that you could convert between different literals pretty easily just by updating how you want it to be converted. All right. Um, Now, please remember that that although this stuff is working in a REPL, all right, when we convert it this way, as you saw here, equals blah, this will not necessarily work inside of a source file because of monomorphization. So basically, we need a concrete type in order for it to actually work. And so that would make things a little bit difficult. All right. Now, you saw that there was a text type using import data.text, as you can see here. There's also a byte strings type for dealing with byte string. These different types are distinct types, all right? They're disjoint. So if you made an A equals blah and make this a text type and made a B that's a blah and made this a byte string, these are treated as two different types. So A equals B is not going to actually convert, all right? And that's an important thing just because of the fact that there might be some things that you may want to have as um, a uh, a string literal or a text literal, and some things that you want to have um, a a byte string literal, even if they are on the underlying same value. All right. Just because of type safety, you want that conversion to not be implicit, but you want it to be explicit. All right. Um, this adds the side benefit, of course, of um, not having to wrap each literal that you've converted into a particular type, like using from string. All right. So let's go through a couple of these things here. So each of these imports here are doing what's called partial imports inside of Haskell, all right? With the exception of the qualified ones and we'll touch base on that. The imports look much the same like if you're using imports in, say, Python, with the exception that instead of saying from module import whatever, you do import the module name, and you just specify what symbols in parentheses that you want. We've actually covered this before in a previous episode. I'm just kind of mentioning it again as a quick review. The one thing that's new here is this import qualified. Uh, you may remember, or you may have used in other languages, like say Python or in um, using C++ or anything, that you have this way of taking a namespace and associating a new label associated with it so that it's easier to type, for example. So like you wouldn't necessarily want to call out uh, byte string char 8 has BC. You won't have to call out data byte string char 8 everywhere. Instead, you could just say BC everywhere and it will actually mean the same thing. All right. But in order for you to do that, you have to say that we're qualifying it has this particular symbol, and that's what the import qualified is. All right. Um, the replicate M and lift IO stuff that is dealing is more extensions on top of the IO monad. The replicate one is actually more of replicating specific monads to go from one form to another. We may not uh, And oh, there's one more thing I forgot to mention about qualified names. Qualifying the import also means something in terms of uh, uh, how it's written inside the code. All right. Uh, Members and functions and types that are members of a particular namespace that has been imported as a qualified namespace or a qualified module must be actually associated with the full module path, meaning the alias that you provided has to be the starting point in order for you to actually um, call out that particular type. So in this case, you have bc.bytestring, bc.bytestring here, all right? You're not talking about any other byte strings. There might be other byte string classes. So to differentiate it, you're basically saying that you're qualifying it to the full module path, so that way the lookup is straight up. All right. Um, when you are calling out, say, pack or any of these external symbols that are part of that qualified namespace, this actually expands when compiling to the fully qualified namespace, meaning in this case, BC will when compiling expand itself to data.bytestring.char8, and then you'll end up then calling out and grabbing the bytes, the particular type there, in that case, the byte string. All right. Um, Whenever you see a function like sorry, an import like this, you're actually importing everything. This is like a what's it? If you're For the Pythonistas that are following along, this is like a from module import star. All right. Not usually a good idea, just because you might shadow a bunch of functions that other things are. But if you are very careful and know what you're doing, it can actually make things a little bit easier and a little bit cleaner. All right. So just always use caution when you see those kinds of stuff. All right. Um, let's find something that's related to. Okay. Okay. So this one is the one that I wanted to go through. Where is it? Um, Not the connection. Um, okay, let's start with this. So, first we want to grab some random element, which we have to define a random element generator. So, given some random string, we will grab some sort of character from that string, and then that's considered to be a random element. Now, the one thing that you might end up recognizing here is that we are defining each of these as IO elements. So, shorty gen is an IO string, random element an IO string, our save URI is IO related. That's because Scotty ends up using these in order for it to actually go in and return a particular uh, a particular value to the underlying socket that we're actually wrapping around. All right. So Scotty actually internally opens up a socket on a port, as you can see here when we specify the port number, and then it will go in and it will take that connection and then specify some URL mappings here. And what this does is anytime you specify this mapping or get this mapping from a curl request, it will go in and execute the actual um, type here, the actual value of this. All right. And to see this, I thought it would be probably useful. And let me see if my shell is done here. Yes, it's done. Okay. Let's go ahead and do a type on the get. All right. So what this does is um, everything in Scotty actually takes in a monad and returns a monad. All right. At least when it comes to route patterns. Okay. So in this function here, this get post is a similar thing. You're going to take an action monad, probably internally is going to be reading in from the socket that has been wrapped around, as you can see indicated by R dot connection, and R, as you recall, is us grabbing stuff from Redis. All right. And what it's doing is it's probably reading in from Redis on the socket, and then that action is then used to call out and return this Scotty unit, which is then passed into the do syntax, which unwraps using, if you remember what it does is this param URI. It's unwrapping the internal state of the Scotty object, which is in this case a unit um, recognizes that, and it then internally calls out to using the type signature param, uh, some text that's probably provided by the underlying socket, and returns that URI into uh, this value that's then later on parsed when we unpack it. Okay. So a lot of this stuff here is moving actions along, all right, that internally keeps some state, but it ultimately returns. So if you do a get at here, you will see, um, let's just do type. Let me see this. Scotty. And then do an app con. Let's see what this do. Oh, right, because I don't have Redis. I can't actually run this. Let's see here. So let me see what this does internally. What does tr.connect do? Grabs a connection info and creates an IO connection. Okay, so we unwrap the IO connection. So we have a r.connection object here when we call app archon. App archon then grabs the r connection and it uses it later on internally to, what does this do here? This, here we go. So this guy basically takes the Redis connection and it saves in Redis the shortened URI and the return value is then lifted into a response that is then written out to um, the uh, HTML value. So it has an HTML response. It's going to take shorty created, which we actually, I think, defined it earlier. It takes a response and it will pack the response with the actual URL now. And this link shorty is something that we wrote earlier too. Um, and specifically, it goes and creates uh, the actual, since this is an HTML page that we're writing to, it is creating the actual anchor, the hyperlink anchor that you would normally see in the HTML. All right. Now, um, what's important to this here is this is actually a typical function. Okay, all this is doing is a reduction. It's a catamorphism that's taking in a list and it's returning a list of different strings and returning in a string. All right. So this join operation we've all seen before, and we can always love. The important thing to see from here, though, is this shorty created instance as well as the sequences stuff that's happening behind the scenes. For one thing, notice that we can map different connections using Scotty's APIs. And what we'll get in return essentially is a Scotty monad that will allow us to move along and take a Scotty unit and then essentially draw. In many cases, we're not actually using the Scotty unit, the unit that's returned, because it's a unit operation. We are actually uh, moving it along to the next sequence operation that's happening behind the scenes. So in this case here, we have one sequence operation, which is the case of dealing with the root URI, and the second one is if we provide a shortened URI, how do we handle that? All right. The rest of this, I think we've already talked about, at least with respect to monads, what's happening here. All right. We are dealing with the unwrapped type of um each individual object that we're actually getting from the lifting operation. And we end up using that unwrapped type to actually go and do some logic around it. In this case, the lift IO function that's provided to us by control monad IO class that actually takes an object and it will actually create the underlying monad of that object. So in this one here, what we're expecting is from get URI, which returns an iter type. All right, and I don't believe we define. Oh yeah, we do define it here. Okay, we are actually taking that iter type, wrapping it in an IO function, and that's because of the fact that the actual run Redis, no, no, not run Redis, the run get call the r.get, that actually returns an IO object. All right. So if you're seeing what I'm doing here, I'm sorry. Okay. So if you're seeing what I'm doing here, I am doing nothing more than um, looking at the type signatures to see how things line up. Okay. At a high level, all this is doing is a series of IO operations that are happening in sequence. Okay. Internally, each function call that's actually creating an IO operation is then passed in to a function that takes in uh, a more primitive operation that is the actual underlying value that's wrapped in the IO type. All right. And it's going to return at the very end a Scotty monad unit. All right. That Scotty M unit is the only thing you really need to kind of look at the very end of this function. Everything in between, you need to make sure all you have to know is in the do syntax, each sequencing operation, it's going to first lift the value, whatever values you have, into the monadic world if it needs to, do some transformation on it, unwrap it, and then return it when it does the this this left arrow assignment. All right. That's the only thing you really need to look at. The rest of this is basically the same stuff that we've been covering for weeks now. All right. We have a case statement, a switch statement. We're looking at the pattern matching on the iter type, and we're ignoring in this case everything that's passed into just. Um, and all we're doing is we're actually going to then run another series of monadic transformations, specifically dealing with the shortening of the URI before returning it. And then in the case of the second case, we are using the iter type to get the URI from Redis, and we are essentially depending upon the either values as indicated by the fact that the switch statement is being left or right, we will end up running some comparisons and actually retrieving either the appropriate value that's stored in the HTML, um, or we'll say that the URI is not found. All right. Um, the best way to actually look into this, if this may sound confusing, is literally line up the types. All right. And once you line up the types, the only thing you need to worry about now is remember that the magic of the do syntax is it does a sequence, then a bind, and the bind does a concatenative map and returns whatever the it will return a the top level monad instruction with the flattened value inside of it has its value. And at the REPL, once the series of monadic transformations are done and you've actually finished binding, it will actually unwrap the underlying value that the monad is representing and return that to you. In the case of if you're writing this in a file, you can certainly return the monad, all right, to make that function another transformation that's part of additional transformation pipelines. So as you can see here, app can actually have a series of monadic transformations that unwrap whatever values that's coming in from Scotty. Um, but we're using IO to handle a lot of that because we're leveraging Redis behind the scenes in this particular example. I'm going to pause a minute and see if there are any questions. Honestly, this is the essence of this chapter and what we've been covering the last few weeks. Okay, I know this is a short episode on this, but it's very important that if if things are confusing right now, before we move on, for you to rewatch anything that you find confusing, all right, and get a sense of how to actually read through this code. The reason is what we're covering in the coming weeks is going to be essentially applications of this. All right. We're going to be looking at other type classes. Specifically, in the coming weeks, we're going to be looking at the foldable type class and traversable type classes. Um, that both expect you to understand what monadic transformations are. And then we're going to end up dealing with the reader functor and well, it's the reader type class that has some interesting properties with regarding to reading in values and how to return them. The rest of these type classes that we're going to be covering up until our discussion on parser combinators are essentially type classes that all deal with either monads or applicatives, if I'm not mistaken. Yeah, they're either monads or applicatives. So to give you a taste of what we'll be talking about next week, which is covering chapter 20, is I think import. I thought it's foldable is in. Oh, sorry, not type. I foldable. The type class. Foldable is something we've already looked at before. Foldable is dealing with reductions and catamorphisms, and traversable is a type class uh, dealing with iteration. All right, which is why it needs to have some sort of functor defined for that particular type. All right. Um, that's it for this week, really. If there aren't any questions, I again apologize for the lateness and tardiness. Um, uh, Next week we're going to be covering the foldable type class. The week after we're going to be covering traversable and so forth. Um, and I think at this point now we all have the foundation to really start looking at libraries and start doing some practical stuff. Um, And before we finish the book, I may end up just taking a small break from reading the book to check out some of those things, particularly like what we saw before, like Scotty and Spock and all this. But I haven't decided on that. Stay tuned for that. I'll probably throw an announcement up on Twitter. If you guys are following him on Twitter on Unix Nerd, that's spelled UNXN3RD. I'm also Bugram on the Lisp Discord server, as well as the Functional Programming Slack channel. Before I let you all go, just a standard reminder: Atlanta Functional Programming is looking for speakers. If you have a topic functional programming related, by all means, drop us a line. It can be in any language. We are a language agnostic group. We're trying to promote the use of functional programming as a way of designing APIs and subsystems and larger scale systems. Um, and let me know either via Twitter or Meetup direct message or Lyft Discord server or Slack. You have many avenues to contact me and my co-organizer Judd, and we will get you scheduled. Um, so stay tuned for next week on chapter 20. And I hope you all have a good evening and rest of the week. Thanks.